All right. So what I want to talk about, again, like I said, I want to motivate the idea of circuits from what we've talked about in terms of electrostatics, right? So we've talked in electrostatics, we've talked about positive and negative charges. We've talked about how in the conventional model, you think about positive and negative charges as things that can move and attract each other. We talked about how in reality, what's happening is these negative charges arise from the electrons in atoms, and then a positive charge arises from the nucleus of the atom when electrons have been separated. And then we talked about like how they attract and repel. And the most important part that I want to talk about is last time we discussed electric field, right? And we talked about how an electric field is a way to solve the problem of action and distance. It was strange to think, how is it that a positive and a negative charge that are not in contact with each other anyway, how is it that they can have an influence on each other? And we said that the way to think about that is we think about them having an influence first on space, and they cause an electric field to arise in space, and then the other charge interacts with that electric field in such a way that that's how the influence gets mediated, right? So with that idea of the electric field, I want to talk about how a battery can make an electric field, and then how we can harness that electric field to get a circuit. So what I want to do first is I'm just going to start by drawing a basic battery here. And I'm going to start with a battery works with the magical power called chemistry in the inside of the battery. And but I don't really care about the chemistry. So there's chemistry that's going on in the battery, but take a chemistry class to learn that. What I'm interested in is what happens as a result of the chemistry. Is you end up with the positive charges being pushed to one side of the battery, and you end up with the negative charges being pushed to the other side of the battery. So that's in essence the chemistry of a battery. Its purpose is to separate the positives and negatives. Now, vaguely, I'll tell you that this works through ions in the battery. And what are those reactions called? Redox reactions. So the chemistry redox reactions. You need to balance the charge. So a redox reaction is kind of, as my very poor understanding of chemistry goes, my understanding is that that's where this comes from. You also maybe in chemistry have talked about cathodes and anodes. So in essence, a battery has a cathode and an anode, and the chemistry sort of allows the positive ions to congregate at the cathode and the negative ions to congregate at the anode. But again, I don't really care about the mechanism here. I just want you to know that there's some magic of chemistry that goes on in the battery, and this is what happens. You end up with positive charges on one side and negative charges on the other. Okay. One of the ways that we measure how much the battery does this is with something called electric potential, or more commonly voltage. And voltage at the core of it is a measure of electrical potential energy. This is I'm skipping over a little bit here. What actually happens is potential energy itself is going to be something that occurs between two charges, and then voltage is like if you take out one of them. So just like we had, remember how we talked about electric forces are between two charges, and then an electric field, you can think about one charge as making an electric field. It's the same with voltage. That was chapter 17 that I decided to skip this year so that we could get here. But the basis is you have two charges. As you pull those charges apart, right? You pull the positive and the negative apart. It's kind of like a rubber band if you think about it, right? I'm storing potential energy because those positive and negatives really want to attract each other, right? And since they really want to attract each other, me pulling them apart is storing potential energy in them. So you think about potential energy as being stored between charges, and the voltage is kind of what's in one of those. But that's kind of the idea here. So you have this battery that creates some voltage, and then what you're going to do is you're going to take this battery and you are going to take something that's conductive, usually a wire, right? I want to draw this. I'm going to draw my wire as having a little bit of thickness. So we're going to take a wire or something that conducts. And then what we're going to do is we're going to make that wire really thin. Put it through a really thin coil here. And then we're going to take a wire and go back to the other side of the battery. And this here, I'm gonna put this coil of wire in a gas-filled bulb that is separated from the environment. And here's going to be our most basic circuit, but I want to go into what happens to make this happen. So again, what we've done is the magic of chemistry has made there be a lot of positives on this side of the battery, and it's made there be a lot of negatives on this side of the battery. And the result of this is that, again, we talked about those charges want to attract each other, but it turns out that it's much easier for them to move through a conductor than it is through an insulator. And air is, for the most part, an insulator, right? For the most part, charge can't travel through air until you get enough charge that you can get a spark, right? So if you can't build up enough charge to get a spark, the air is not going to let the electricity through it, or it's not going to let the charges through it. But if you've got a conductor there, it will, right? So now these charges are going to try to attract each other, right? And the result of this is you make an electric field, but the electric field, because it's easier for the electric field to be propagated through a conductor than it is through an insulator, like the air around it, the electric field stays in this wire. But again, the electric field, if you remember when we talk about the direction of an electric field goes away from the positive charges and it goes toward the negative charges. So what happens is by connecting the two ends of this battery with a conducting piece of metal, right, the wire, what I do is we're making an electric field in the wire, and that electric field is going to tend to make the charges go through the wire, right? And that motion of charge is what with what we're going to call current. So we're going to define a new term here called current. So current, and for historical reasons that I don't recall, the symbol for current is a capital I. But current is going to be the rate that charge flows. So we can give it a mathematical definition. We can say that current I is defined as how much charge, the change in charge divided by the change in time, right? It's how much charge flows through a given point in a given amount of time. So what's happening here, right, is we set up an electric field in the wire, and that electric field is going to cause those charges to move. The rate at which those charges move, we're going to call current. Now, what's happening is, so if you think about all these charges that want to move, what I've got here is the old style incandescent light bulb, right? So old style incandescent light bulbs, not these ones that are up here, and not the ones that you can buy at the store nowadays, the LED lights or the CFL swirly bulbs. Not like those, but the old style bulbs, right? Which is kind of what I've drawn here, which is there's a glass bulb, and then there's a very thin piece of wire between two contacts in the bulb. And what's happening is you have a current, right? You have so much charge that you've got to force through this really tiny wire, and you do that so fast that it heats that up and causes it to glow, and it causes it to glow, and let off light that we can see. And sort of that's the basis of an incandescent bulb, is that you're taking moving charge and you're forcing a lot of moving charge through something very small, so much that it heats it up and makes it glow. All right. What I want to talk about here is I want to be clear about terminology. So again, currents were understood before the atom was understood. And so usually we consider current as going positive to negative, right? This is the direction of the current. And we're going to call this is actually called the conventional current. So by convention, this is the current we have, but this conventional current, conventional current. We talk about conventional current is what are the positives going to do, right? Just like we've talked about everything else in the conventional model, right? So conventional current moves from positive to negative, right? It goes this way from positive to negative. Like I said, we know now that that's not really what happens. Really, it's the electrons that are moving. So there's something else called the electron current. And the electron current moves against the conventional current. Again, so the idea is it's the difference between what's actually happening and the way we think about it, right? The way we think about it as positive charges that flow through the wire going from positive to negative. That's how we usually think about it. That's called conventional current. But what's actually happening is it's electrons, which are negatives, that are going the opposite way. And electrons go from negative to positive. Yes.
Why haven't we changed the way we think about it? We know that what would be kind of wrong.
Well, let's be clear first of all, it's not wrong per se. Conventional current is a perfectly fine way of thinking about things that explain the macroscopic, like the things we can see, microscopic. Yeah. Explain the macroscopic what I would say to that answer, like I said, the problem is that it is so, like electricity was such a well-established science before the atoms were understood that there's just a lot of inertia there. I mean, it's kind of the same sort of thing. Like you ask, why haven't we in the United States stopped using the imperial units yet? Right? Like, although I think that this even makes a little bit more sense than why we haven't used imperial units. But like, can you tell me how long a kilometer is? I can't tell you that. It's so there's so much built up inertia to this way of thinking. Okay. I got any questions at this point? All right. So what I'd like to do now is I would like to hand out some lab material so that we can go a little bit further with this. One thing I had forgotten to do earlier that let's just add real quick is let's add the units in here, right? So the units of volts, it turns out the units for volts are joules per coulomb, but we summarize it with the name volts, right? So usually the unit we'll use for voltage is volts, but it's technically joules per coulomb, right? The units, what do you think the units for current are going to be? Well, charge is what? Coulombs. It's going to be coulomb per second. And we give this the symbol capital A, which stands for amperes or amps. So that's the symbol, or that's the unit for current. So now I want to look at what we saw in the lab. We saw in the lab that if I graph my voltage, sorry, I did that backwards. We graph current on the y-axis, right? So I graph current against voltage here. So if this were perfect, we'd have something like this. Where, which one's the one bulb? This one will be one bulb. This one will be two bulbs. And this one will be three bulbs. So what does that mean? That means that current is going to be proportional to volts. So what I'm going to say is that I is equal to some number. So I'll call it like the slope times volts. So if I say like y equals mx plus b, if b was 0, y is the current, x is the volts. So we're going to have current equal to the slope times volts. Or it turns out that if we say that the slope is 1 divided by this thing called resistance, I'm going to write that the current is equal to V divided by R. This is going to be what we're going to call Ohm's law. And Ohm's law says that your current is going to increase when you have more volts, and it's going to decrease when you have more of this thing called resistance, right? Now, in our circuit, where did the resistance come from? The bulbs. The more bulbs I had, the more it resisted current. So we need to find one more thing here. We need to find resistance, which we're going to use the symbol R. So resistance is going to be opposition to the flow of charge. And its units, if you think about the units it has to be, think about it for a second. Its units are going to be volts per amp. And it turns out that we give this a symbol, and the symbol we give is a horseshoe. It's the Greek letter omega, and it stands for ohms. Ohms are the symbol that we use for resistance. Yeah. So the idea here is this equation, I equals V over R. I equals V over R means that the current depends upon your voltage and resistance. Your current is directly proportional to voltage, right? If you get more volts, you put more batteries on, you get more current. That makes sense. Current is inversely proportional to resistance, right? You've got more things to resist it, right? Then the current's going to move slower. In our graph that we made, how is the slope going to be related to resistance? Yeah. It's what? Close. Our slope isn't volts over amps, though. Our slope is amps over volts, right? So if you take a look at this equation, if we say that the slope is 1 divided by the resistance, this works, right? So to find the resistance of 1 light bulb, 2 light bulbs, and 3 light bulbs, you're going to take your slope and you're going to take the reciprocal of your slope. So that's the last thing you need to do in your lab. Now, I want to look at what would we expect if you found those 3 numbers for resistances. Could we predict how they should be related? Like, let's say that you did the first one and you found that 1 bulb has a resistance of 2 ohms. What should the resistance of 2 ohms be? More than 2 ohms, but how ohms in particular? How many ohms in particular? They're all the same. It should be 4 ohms, right? So if you found 1 was 2, then your resistances should be 2, 4, and 6, right? If you found 1 was 3, then it should be 3, 6, and 9. So we're going to see for number 5 how close you get to that happening, right? So if you calculate your resistance for 1 bulb, 2 bulbs, and 3 bulbs, we're going to see how close you can get to some sort of pattern like that, where the resistance of 1, the resistance of 2 is twice the resistance of 1, etc. The problems are very straightforward. So there's this equation, I equals V over R. The way you'll see it on the equation sheet is V equals IR. These mean the same thing, right? They're just rearrangements of the same equation. So, for example, I could give you the voltage and the resistance of a circuit and ask for you to find the current, right? Or I could give you the current resistance, ask you to find the voltage. So it should be pretty straightforward. But like I said, you can now do chapter 18 and chapter 19 is canceled. All right, if you would do me a favor and